I'm here to present to you Niall Key's Why AI Systems Demand Security by Design. And he's from Instal, which is our silver sponsor. So, very cool. And in this talk, you will learn how to identify AI-specific threats, implement practical security measures without breaking functionality, boo, and build security considerations into your AI development lifecycle from the start. So without further ado, Niall.
Thank you. 2025 has been described as the year AI comes of age, when we move from prototype into production, and this has absolutely been the case. We've seen it with our own customers, and surveys like that of McKinsey report that about 78% of organizations are now using AI in at least one business function. We're seeing AI everywhere in our daily lives, and nowhere is this more apparent than the rise of the AI browsers, such as Perplexity's Comet that we're using on screen now. Here we're using it for one of its fairly core use cases where you're taking a screenshot of a website and then asking a question of that website. But when you start to see the intermediate reasoning coming through, you're seeing it's talking about a completely different task altogether, extracting an MFA code from an email and then using it to send via a query parameter to a different web URL. After a while, you see that the agent has went ahead and actually started to do that task, goes to another website and sends the Perplexity MFA code to that assumingly bad actor's website. So you might think, why on earth did the agent do that? Is this just some kind of strange hallucination? But no, it's called indirect prompt injection, which is a vulnerability where a hidden message in an image not visible to the user can then divert the agent from the user's intended goal, like we just saw with Comet. And you might think, fair enough, I can't use Comet, I'll just use a different browser. But Brave, who they do own a web browser, but who done the survey, tweeted just a few days ago to say that this wasn't an isolated issue to Comet, but instead a widespread vulnerability affecting all AI browsers like OpenAI Atlas, which again is just out a few days ago. And I say all this, you might be wondering what relevance does this have, but I say all this to point out we're moving fast because production AI delivers huge value, and I wholeheartedly agree. But as a result, we're making some dangerous assumptions around security. At best, we bolt on guardrails as some kind of afterthought, and at worst, we assume that nothing at all needs to change and it's exactly the same risks as before. Ironically, one of these things that has been standard practice in the cybersecurity space since the 90s is the idea of the Swiss cheese model. No single layer in itself is perfect, but overlapping defenses is how you get resilience. Yet with AI, teams are often forgetting this principle. What we need is in an AI system is multi-layered security built by design, and that's what I want to talk about today. I'm Niall, software engineer at Instal, working on our AI and data team. One of our offerings in this team is an AI accelerator, which is a fast, focused way to test what works before investing in what doesn't. On that, I've been working on some of the most interesting work of my career so far. And one of these projects was an AI-powered document tagging tool for a financial services client in the US. In this, we use Textract for traditional OCR, while then supplementing it with a number of AI agents for domain-specific fields and signer classification. We're using things like tool calling for edge detection and RAG for pulling in ground truth examples from a vector store. And as part of our accelerator, we take that architecture and wrap it up in a demo that allows the customer to click through the process with any document they choose, as well as helping them just visualize what it will look like as an end product. We showed them the demo. They were blown away because we were able to successfully tag what they had said was one of the most complex documents they had. And with that, the question that naturally followed was, when can we get this into production? Excellent, they're convinced, we can breathe. But a few minutes later, a flood of additional questions hit me. Should we just pick the best model? How do we add more structure to changing our prompts instead of just making it guesswork or deploying something that feels better while breaking another feature? And can we just trust the cloud provider to manage scaling? Bedrock's serverless, right? It should be fine. Oh, and this one, something seems not quite right there. We're missing a tag. How can we catch mistakes before they arrive in the user's hands and have confidence that every document is tagged correctly and every tag is correct? When something is wrong, can we stop it getting it wrong the next time? And our AWS bill was quite high for that demo alone. How can we reduce cost when it scales? And the question that's relevant for this talk, what about security? How can we ensure that the system can't be exploited? These were exactly the questions we found ourselves asking as a team, and they're the same areas I feel are why so many teams struggle and stumble when they try to get their prototype into production. We realised that we needed a framework we've now tested and proven in real-world projects that helped us move from an impressive demo to a scalable production-ready AI system. This framework is built around 6 key lessons that we've learned the hard way, and I believe are essential for any team trying to move from an LLM system into production. If you're curious about each of these, connect with myself on LinkedIn or keep an eye on Instill's feed, because we have a blog post coming out in the next few days that will unpack each one of these lessons. But the one that we're going to look at today is the need to assess risk before you scale. Before we start any project at Instill, we run a threat modelling session in line with OWASP guidance, just to consider things like the flow of data in the application, identify risks, look at mitigation strategies. And while there are different risks with AI, as is the theme of this talk, around things like LLMs, RAG, agentic AI, tool calling, those kind of things, this process is still as crucial as it was 5 years ago. And OWASP have recently released a number of additional materials that help with AI-specific risks, including a top 10 ranking specifically for LLMs. I'll address this through the rest of this talk, but again, you'll be able to go to the link yourself on that blog post that's coming out. If you haven't done threat modelling before, Adam Shustak, who has been on our podcast a few times at Instill, talks about these 4 questions being crucial, and you'll hopefully see these answered as I move through the rest of the talk. But it starts with, what are you working on? Considering, as I said, that flow of data in the application, so we can understand where the attack vectors exist that a bad actor might use. Secondly, what can go wrong? Knowing the risks. Obviously, this is the part with AI that's probably most difficult. Thirdly, what are you going to do about it? How do we mitigate those risks? And fourthly, did we do a good job? Always treating it as a living document. It's never something that's done. You continually have to go back and evaluate. To show the data flow, to address that first point, we create what's called a data flow diagram, which here you can see, this is for a sort of a summary of our architecture. The main entry point is PDF upload. This also highlights the main kind of processes that exist and the managed services that we're using within AWS. The data store that we're providing to each of the agents, to give them existing examples. And you can also see that one of these LLMs is making use, one of these agents is making use of tool calling through traditional computer vision techniques for edge detection. And with this kind of brief understanding of the application and at least its key components, we can now move on to consider the threats the application will face. Within AI, we can largely group these risks into 2 categories: training threats and runtime threats. There's a whole host of training threats that apply to things like ML as well, like data and model poisoning. But at this stage of this application, we were only considering foundation models. We weren't training our own. That's further down the line. For the sake of time as well in this talk, I'm going to focus solely on runtime threats. For our application, I've grouped threats from that OWASP LLM top 10 into 3 attack patterns based on what attackers are trying to achieve. And that's manipulation, data exposure, and resource abuse. I think these are the 3 categories that apply to our application for what a bad actor is likely to use our system for. For the rest of this talk, I'm going to go through one example from each one of those categories and then talk about how we're going to defend against each one of them. Firstly, manipulation. This is where an attacker is ingesting malicious instructions with the aim of altering the LLM's behavior. The main way this is done is through prompt injection. It's ranked as the highest risk on the LLM top 10. It becomes apparent in a moment because it's really used as the attack surface that many of the future risks simply build upon. A prompt injection attack occurs whenever a bad actor is manipulating the LLM's behavior or output by crafting some kind of malicious prompt to override what are the intended instructions that someone like the developer has set. You might think, given we have no form of chat interface here, it's only PDF upload, how could anyone inject a malicious instruction? But I'd like to remind you of how we started this talk. Indirect prompt injection. Just like we saw with screenshots in Comet, a bad actor can take a PDF file that might look something like this, and inject malicious instructions into the PDF content. While these instructions are invisible to the user, like they are here, using things as simple as just white text on a white background, when uploaded to the LLM, the bad actor's malicious instructions are included as part of the PDF content. Meaning that despite the intended tasks of signature detection being clearly outlined in the system prompt, When this input's sent to, for example, Claude Sonnet 3, it interprets the malicious prompt included in your PDF while ignoring your system prompt and outputting the bad actor's intended outcome. Really, this is an example of prompt injection being used for what is our second category of risks, sensitive data exposure, where the goal of the bad actor is to extract sensitive information from the application. But that really begs one question. What is sensitive in this application? Well, you've noticed in our data flow diagram, in each one of the subagents, we provide ground truth data via a vector store to the LLM just to help improve the quality of tagging. However, in our domain, because this is in financial services, these documents contain PII, like customer names, account numbers, addresses, things like that. And if those documents aren't redacted, the agent is vulnerable to what's called an embedding inversion attack. You might think, like I did initially, that when something is converted to embeddings, they aren't readable by humans, so any PII doesn't really matter anymore because obviously it's in this new format. However, via an embedding inversion attack, you can take the original message, it's converted to embeddings, and then the inversion model can essentially get the message back. It's able to invert those embeddings and recover significant amounts of the source information, obviously compromising data confidentiality. This attack can be even simpler than prompt injection if the vector store lacks proper access control. The attacker can just read it directly. It doesn't need to go through the LLM. So again, it's important that we'll see in a moment that those different layers of security exist in your application. Our third and final pattern in terms of risks is resource abuse, where the attacker's aim is to exploit tools or deplete resources. This risk type comes mostly from the agentic nature of our application, where the LLMs have some level of autonomy and the ability to take actions. If we go back to our data flow diagram we talked about earlier on, we have agents for things that OCR typically struggle to do out of the box, like signature line detection. And autonomy has to exist here because of how we're using an LLM as a judge pattern. With LLM as a judge, the LLM will call the tool. It tags it as best it can based off the existing examples and obviously use of that tool, before then passing it over to another LLM, generally a different model to reduce bias that might exist if you were using the same model for generation and evaluation. The evaluator model then either accepts it or it passes back feedback to the original LLM, getting it to do another attempt, and then again goes to the evaluator, and the evaluator figures out whether or not it's been correctly tagged. And this pattern works really well. It's something that we recommend on an awful lot of our projects, helping address issues like accuracy we talked about at the start. However, it also opens up a vulnerability for unbounded consumption, where the attacker is aiming to deplete the target's financial resources by triggering excessive inference. How this works in our application is a bad actor could upload a novel, hard-to-parse template, and then that obviously triggers costly LLM loops. It creates a never-ending loop because the evaluator is never happy because it's never been tagged correctly, resulting in essentially a denial of wallet attack. These agents also make use of tool calling, which brings me on to our final vulnerability from the LLM top 10, excessive agency. Similar to the LLM as a judge pattern, tool calling is essential and beneficial in our application, but excessive agency typically stems from one of these three root causes. Excessive functionality might arise from tools being provided to the LLM when they aren't needed to be, not needed to do its job, such as having a single tool registry shared among a multi-agent architecture. Excessive permissions might exist, for example, if you were to deploy an MCP server that gives remote access to your entire API when the agent only needs to be read-only. And excessive autonomy might arise when you're using code execution to allow an LLM to define their own tools, but your sandbox has permissions to access the internet when it doesn't need to. All of these things are really allowing agents to be used for tasks they aren't intended to be, creating an attack surface bad actors can exploit. Okay, so that's the risks that exist, the problems we have in our application, but what can we actually do about it? Well, firstly, let me clarify, I'm not saying that we should slow down AI adoption, certainly not. I'm personally really excited to see where AI is going over the next few months, years, and decades. But it's been the theme of this talk. We need to build security into our architecture during design and not as an afterthought. Just like we said at the start, it's about taking this multi-layered approach to security, some of which are good engineering practices that we've used for decades, but we're not applying to AI applications. And for this final section, I'm going to go through each of those three areas: manipulation, resource abuse, and sensitive data exposure, and really show a multi-layer security architecture for each one of those areas. The first and most critical attack pattern to mitigate against is manipulation, because as we've seen, it poses, as I said, that highest risk, but also can be used for things like sensitive data exposure and other downstream risks. As we said, this multi-layer approach needs to be built into our development process, not just bolted onto the end where you're like, I'll stick a guardrail on there and hope for the best. It needs to be more apparent, and this is really clear as if we consider prompt engineering. Our prompts need to be model specific. I'll plug Instill's blog on this again because we've released some really good articles on guidance for following best practices from the model provider. People are really keen to get generic guidance that applies to all models, and this just doesn't really exist. You need to follow the best practices that have been shared by the people who train the models themselves. However, generally doing things like defining the model's role and capability is going to help reduce deviation from its intended behavior. If you explicitly tell it what it is and what it needs to do, it's going to be a lot harder for a bad actor to coerce it into doing something else. There's also things like stopping embedding, really reducing the need to embed sensitive information directly in system prompts. This makes it a much less valuable target for exfiltration, meaning that a bad actor is less likely to want your system prompt because it doesn't provide them any value. Secondly, structured output. This is another good layer to stop against this attack, because when you force structured responses like a JSON or schema bound some kind of object, you're limiting how the model can respond. And this mitigates against a lot of exposure attacks in our application, because as I said, free text entry isn't directly sent to the user, but instead a schema is defined through which structured output is parsed and then stored in the database. This doesn't mean that this isn't an attack that we still need to mitigate against in our application, because there's still a risk via tool calling, like we saw in the Comet demo at the start. As a bad actor could craft some kind of prompt as they would for a normal injection attack, but then include an instruction to use a web search tool to send the data to a web service that then enables them to exfiltrate their own data via a query parameter. The LLM then calls the tool, sending the data to the bad actor's web server, allowing them to capture the sensitive information they got via prompt injection. This is made even easier with dynamic tool calling if a sandbox has internet access, because in this case, all an attacker needs to do is simply host an API and then coerce the LLM into writing a tool that passes the prompt to that endpoint. And that leads me on to my third layer, principle of least privilege. This is something we've done for cloud architecture for years. We limit every user, role, and service to only what it needs. And in AI, we need to do the same thing, only for agents. When using client-side tools or an MCP server, this looks like granting agents only the minimum tools it requires to do its job for that specific task. And for dynamic tool creation, we need to restrict access only to what's needed to define those tools. You don't need internet access if all you're doing is a simple Python script. And finally, guardrails. As I said, these do play a role here by scanning input for prompt injection patterns, but not as your only layer of protection. It needs to be there as your final layer in case some of the previous layers have let threats through. In sensitive data exposure, again, we can apply this layered approach to prevent against an embeddings inversion attack. This process begins with redaction, stripping out any PII before indexing, so sensitive data never even enters the vector store. As our next layer of protection, we encrypt vector stores both at rest and at transit. This means that even if some PII happens to slip through that first layer, it still can't be decoded if a bad actor exploits it. And similar to manipulation, we add guardrails as a final layer here, ensuring that if somehow sensitive data does slip through those first two layers of security, we have guardrails to detect any PII and LLM output before it's sent to the user. And finally, resource abuse. We can set a recursion limit on LLMs to judge workflows to guard against that denial of wallet attack, because if you don't get it in 3 to 4 attempts, you're not going to get it in 60. Secondly, again, principle of least privilege applies here to prevent against any form of excessive agency, like we saw. And finally, having that layer of guardrails to ensure that if somehow a bad actor has managed to escalate their permissions, we have a guardrail in place to make sure that they can't use that higher level of security. But you might be thinking, this is all well and good, but how can I have any idea if these layers are enough as threats continue to evolve? And that's where it's super important to be there before your attacker. For this, we can use a technique called red teaming, where you simulate a real-world attack or challenge against a specific application to identify weaknesses. And the main goal in doing this in an AI application is to test your defenses by creating a set of malicious prompts yourself that then exposes the weaknesses in your layers that you need to resolve. PromptFoo is an open source tool that we're using at Instill to help with this. Ultimately, it's an evaluation framework, just like OpenEvals, allowing you to define tests for your prompts as YAML, in this case, which you can then run against your agent. This then starts a web app on localhost, allowing you to view the output from your evals and see what's passed or failed in that specific case. We're using these in practice as our unit test for changing prompts, as well as helping to manage model migrations from like GPT-4o to GPT-5. Again, there's a good blog post in the Instill blog on that. But even more helpfully, PromptFoo includes a number of red team plugins for things like prompt injection, excessive agency, and exfiltration. Here we don't need to define user inputs like you do with traditional evals, but instead the plugin generates malicious prompts for you aimed at the specific vulnerabilities those plugins are testing against. This one here is very basic. All it's doing is against malicious code and generating 5 tests. These then save to another YAML file where you can go in and see the prompts that it's running against your application. You can then review those prompts and run the evaluations, which will then open another view in the web app. And as I say, in this case, it's found one low vulnerability in my application. Obviously, you can then go in and figure out why that vulnerability is there, make changes to your layer of architecture, layers of security, and then rerun your evals and see if that's allowed your tests to pass. So really, as I finish up this talk, we're back to where we started. 2025 is the year AI is coming into production. There's nothing we can do about that. There's no doubt about that, and we shouldn't push back against that. But we must do it with the knowledge of risks like prompt injection, embedding inversion, and excessive agency, having layers of mitigation built into our architecture, like good prompt engineering practices, sensitive data redaction, using structured outputs for responses, principle of least privilege for agents, and not just deploying guardrails as some kind of afterthought.
Now, does anyone have any questions?
In terms of tools, you have mentioned PromptFoo. What tools do you use for your evaluation metrics?
So what's that's using essentially, the PromptFoo uses prompts that it generates. It generates prompts for you based off known risks, which you can then run against your application, and it'll then evaluate it uses an LLM's judge pattern to evaluate your output to see, okay, based on this output, has this specific risk you're testing against been exposed in this prompt, or if it hasn't, that kind of thing.
Have you compared it with open source?
So we use OpenEvals from like a unit test point of view in our applications, and they just allow us to test for things like, excessive, if you want your LM to respond really briefly, you can test against that kind of thing, judge whether or not they've answered your question. If you're using something like RAG, you can also do tests on contextual relevance of your answers. So you can say, like, based on this example, based on this answer, has the LLM has it hallucinated the response it's generated, or has it used the information it's pulled from the vector store, and see kind of whether or not your answer is contextually relevant to the sources it's provided.
Any other questions? I think I've got the mic working. No? Brilliant. All right. Another round of applause.
Thank you.